My microphone is not working. Pause. Yeah, welcome to Coffee Compiler Club. Anything to do with compilers, language runtimes, garbage collection, type systems, programming languages, all fair game. Everyone's heard this spiel before. It's just all old timers here. I think you're live. I'm going to record you and put you on Twitter probably pretty soon. There's a doc in the link. Should be available to people. I haven't checked to see that it's useful, but yeah, it's done with the spiel. Yeah, there you go. People are like hacking already. Somebody even starts out with ideal hash trees. Like there's already a link and we haven't even, okay, somebody say something about ideal hash trees.
Yeah, so we were talking last time about things that were actually immutable versus persistent data structures that are kind of immutable, but they also kind of act like mutable things.
Right.
And usually this happens by turning your array into a tree. And iterating it is pretty cheap because it's logarithmic to get to whatever you want because it's a tree. But if you have to like iterate through the whole thing, if you do something naive, like a for loop at top and then accessing each thing by index, you're going to get really bad performance because now you're doing an n log n thing as opposed to a linear thing. So I'm curious if people have ideas about how do you build iterators for persistent data structures so that I can write code that looks reasonable for element in collection do thing. But I don't keep going back to the root every single loop and having to look at the top again. I mean, you're going to do okay because the high parts of the tree are always going to be in cache and your branch predictors are mostly going to be right as you're iterating through. But you're also going to put a lot of pressure on your branch predictors. And
yeah, it depends on how deep and twisty your trees got, because you'll be bouncing horribly around. I mean, the obvious other way is you have a cached variant of the hot, most not changed in a while thing and a official version that's the whole persistent structure, and you occasionally copy one to the other. But I don't know.
Ideally,
yeah, that's the log structured merge trees technique. Store all your novelty and then slowly bake it into the bigger data structure.
Ideally, you have a pointer that you advance with a, with a simple addition. But, what you said in terms of going back to the root, that doesn't actually happen in reality from a memory point of view, because like in Intel, your instruction is, there's an instruction, is it load effective address, LEA used to be. There's a new one that they built. It LLVM has a super complicated equivalent of load effective address, but it's just a multiply add, if I remember correctly, and it's done, I believe, in less than a single cycle. So your iteration cost on an array, even if you're doing it by index, and Cliff, you'd know this better than me because I'm pulling from like ancient memory, but it's pretty much free.
No, I'm hearing a different story, which is
for an array that will work.
Right.
But if I'm in one of these persistent data structures, I got to chase 4 pointers to get to the leaf.
Right. So you're talking about one of these layered data structures where they've got the
yeah, I've taken your list and said, I could give you an array, but why should I give you an array when I can give you a 64 array prefix tree?
Totally misunderstood the question.
You've got a large shared tree of which there are 15 variant leaves of which represent the delta version from whatever other thing that happened along.
Right.
And as far as I've seen these things go, you sort of continuously add deltas, and so it's only ever a pile of deltas, and you're hanging on to the old ones. And I claim that you need to periodically roll it up, or else you'll only ever be fighting through a sea of deltas, and that will be all your costs. I just was screwing around with these guys doing this database last year, and they were saving everything as a pile of deltas, and I went through and said, no, I'm going to smash it flat eagerly, and then all the iterators become like, fraction of a clock cycle per element instead of hundreds of clock cycles per elements. And it was way easier to smash it flat all the time. So if you have a big structure and you make deltas, you don't want to copy all the time. But if you got little structures and you're making lots of deltas, smash it flat every time.
Right. And most of the times I iterate through. If I'm building up the data structure in the first place,
You want to keep all the deltas while you're building it, yeah.
like,
And then the next time you do a major iterator, it's like smash it flat and then iterate.
right.
Yeah.
So logically, every time I change a leaf, I've replaced the entire path to the root of the tree. But most of the time, my leaf isn't going to escape, and the one up isn't going to escape, and the two up isn't going to escape, and the three up isn't going to escape. And I'm going to build a whole bunch of these things, and I should be able to reuse all those objects.
I'm thinking a different thing, which is the first time I observe I'm about to do a bulk iteration, I'm going to do a bulk smashing. I've played these incremental games before, not necessarily applying exactly your use case. They are highly data flow dependent, blah, blah, blah. The thing that you want to strive for is, I want to say a monotonic, a smooth flow of goodness in shortening all paths, so that at any given scale factor of I have all deltas, I have all squashed flat, I'm only iterating, I'm only deltaing, you always sort of monotonically make progress toward a faster variant. But also end up at the end with a smashed version. So, because that'll be when you decide that you're done making changes, that'll be the version you want. So
as a small benchmark, how can you compare this to splay tree? That I know it's got a tree, but it does what Aaron has said.
Yeah, right. So splay trees are one of the ways people implement these things. So the issue here is, if you're doing deltas, then you want the tree. And at some point, it is common, not always, it's common in the case that you're done making deltas and you're now doing iterators. As soon as you recognize the phase shift, you want to squash it flat, including if you've made it with splay trees or with whatever. Now you want to squash it back to an array. And what I've done in the past is I've observed that it's now being squashed. It's now being, I've now phase shifted and do the squishing. But I didn't do it in an automated way. I looked hard at doing automated, and sometimes you can win, sometimes you can't. So instead, I put a programmer hint in. Hey, right now here, I think I'm done making large delta counts. Squish
Yeah,
it.
so that's what I've seen with the prefix tries is if you expose all the types, the developer can write something that can iterate through the thing relatively efficiently.
Yeah.
But if I just want to expose it as like gets and puts into a data structure,
Right.
I keep finding myself in these n log n's that.
Right. I gave you an extra API that said, and now squish it. And the first thing the gets and the puts did said, oh, I'm squishy. And you wanted them to inline. So for I equals 1 to end of index, get I, inline the first version, which said, if squishy, then go to the second version, which is array lookup of I. Right. And so the for loop said, for highly predictable, always the same test, array lookup. And you got array lookup speeds. And if you weren't squishy, then he said, oh, I failed. Now I do the horrific, recursive tree log, splay log, tree walk thing. And it worked both ways, but you could set the hint. And until you did the next delta change, the hint stuck. So, like all things to do with performance that are programmer specific, they all have the lifetime of a banana,
Yeah, it doesn't give you the nice pass it around as if it's immutable property that the
no, it did. It's just your performance guarantee was you took in log in until you did the extra API call, which said, and now I think I'm not making changes. And until the next change came, you had the linear array performance. At the next change, whenever the next put, you lost it.
So if I have two pointers and one's holding on to the old tree and I call squish.
You have two copies at that point. The squish says, I make a copy of the old tree to a new thing. If ever the old tree happens, I have to whack the fast guy.
So you're allocating memory at squish time.
Yes. Yeah, you can't get rid of the old thing. That's the whole point. The garbage collector can get rid of the old thing. You can't. So, but you can make a new thing that's only there until the old thing got whacked. So it's a cache of the flattened version. And that's made bulk. So it's a little more efficient to make it if you make it bulk rather than you incrementally squish and call and kind of things. Like those all allocate too. And that's probably, what I've seen of Clojure, that's where all your time goes, is memory allocation for continuously doing the delta mods.
Yeah, Clojure isn't actually very good at reusing if I'm 6 deep in the tree and I'm doing something to it.
Yeah.
Basically, the only thing that I'm going to want to mutate is those same 6 objects up to the root. And for the most part, they don't escape. So I could totally allocate them at the beginning of a loop and just mutate those 6 objects in the loop. And then when I'm done with the loop, go, okay, now it escapes and I can't mutate these things anymore. Except Clojure doesn't do that. It actually does a whole bunch of allocation and expects the garbage collector to keep up behind it, which it does remarkably well and only takes about 2x what it would cost to do the thing normally. But
that falls straight into the camp of the garbage collector and the profiling tools are lying to you. So what you just said was exactly a thing I teach in a class, that you get 5x to 10x speedups if you ignore the profiler and the garbage collecting. They're all lying to you and you do the right thing up front. And the reason they're doing it is you're out of memory bandwidth, and it's all young gen collected things, and they all die in the young gen allocator in milliseconds to microseconds. They're super fast to collect. And the direct allocation costs are super cheap, and it's all fresh memory, never before seen by your CPU, and it's 100% cache misses. You're totally out of memory bandwidth, and that will never show except on a hardware performance counter. So all the classic profilers don't show it, and the garbage collector claims he's doing rapid but super cheap GCs, and so the cost looks really cheap, and it's a lie. The cost is really high.
I'm really curious. I pasted a really ugly hack I use where I have a WeakHashMap and I have a soft reference holding the key to the WeakHash.
You pasted where, in chat or in the doc?
The bottom, in the yellow block.
Oh, way down. I didn't go down far enough. Yes. Okay. Yes.
So you see a string there, and you see a string in the value that's actually the key as well, holding it in place. I use that. It makes things go faster. So I walk away.
Doing what though? You're just holding on.
Iterating through lists of lists that are coming from some source.
Are you interning? It looks like you're doing an interning operation.
Well, sure, for the duration of the soft reference, I guess. Plus whatever remnant of the WeakHash sitting around.
I do lots of interning things exactly because the cost savings for memory is not interesting. It's the memory bandwidth savings for avoiding continuous allocation, which turns into interesting numbers. Yeah. I never use weak hash maps because they have other issues, but you know, if you have the right kind of things, they'll still behave. I got war stories with weak hash maps that are ugly.
This is Bollinger, which is recursive of recursive of recursive of recursive doubles. So, you know, you could keep looking up what you did yesterday, or you know, you could expect it to be in a weak hash map.
Yeah. So the next trick is if you're doing endless lookups on strings that are hitting constantly, is you want to not make the string that you're looking up on. You know, it depends where it comes from. If you're reading some big ass file, it's got piles of text. The string is repeated many times.
I'm actually using object ID as a string to hold the double. It's not perfect, but it's faster than going back to the CSV row.
Yeah, so right. So when I parse CSV, so this is from H2O, which is a big data startup I did. World's fastest CSV parser by a very large amount. Like I can outparse anyone unbelievably faster and in parallel and distributed, blah, blah, blah. Main hack, never make a string object unless you're going to stick it. Like it's the first time you've ever seen a string before. Because the allocation on the strings, especially while you're doing a big ass CSV parse, like burn you up. That's where your time goes. So in all those cases, I make a string-like thing. I look it up in a hash table. It's indexed by string-like things. And then if I get a hit, I have a string-like thing in the hash table, which maybe I map to a string, and maybe I just put a string API on my string-like thing. But if I get a miss, I left the string-like thing. It's just a wrapper over the network byte buffer where the CSV bits landed in the buffer. And I just move it forward. It doesn't actually do any allocation for the string lookup even. Like don't even do a string lookup. You do a lookup on a string-like thing, which is just a wrapper over your network byte buffer, your file byte buffer. And that will save you, you know, 2x, 3x your string allocation cost, depends what other things you're parsing in your CSV, is one of the big hacks we did for big performance.
So you're saying like a 8-byte byte buffer is quicker than an 8-byte string to look up?
I'm saying allocating an 8-byte string is costing you 1,000 cycles in a cache miss. Whereas doing the lookup on the two of them are roughly equivalent in a few clock cycles, all totally dirt compared to the allocation costs. Do not allocate the string in order to probe the hash table to see if you got a hit. If you've already made the string because you parsed it in your CSV, and then you're looking to see if you can intern it by looking it up in the hash table, you lost already. It was too late. You made the string, that was your cost. You paid 1 clock cycle to bump the string pointer. You paid a couple clock cycles to fill the string array. You paid 1,000 clock cycles in cache miss.
And this is helping you because the strings are so ridiculously repetitive.
Yeah, but only 50% repetitive is good enough to win here.
And so how are you finding your string rather than recreating it?
You take a string-like thing, has a string-like API, but it backs not over a car array, it backs over your network byte buffer. It has a byte buffer base and an offset and a length. You have a hash table, it's keyed by these things.
And the reason I don't have to allocate my slice into my network buffer the same way I would have to allocate my string is that that's on the stack?
No, the network byte buffer is in some direct byte buffer.
I'm saying you had to make a slice that's like, hey, I'm pointing off to this memory somewhere.
I asked the NIO folks for a byte buffer, which is filled with 8K to how many megs of whatever file, network, whatever packet crap. I take my string-like guy, I say, here's your buffer, here's your offset, here's your length. He's got 3 mutable fields inside. I set the fields, I probe. If I get a hit, and 99% of the time you do, because they were highly repetitive, but maybe it's 50%. If I get a hit, I have one of these things already from the hash table, and that's my winning guy. That's my replacement. And I take this guy and I reuse him. Hey, bump him to the next point with the next offset, and just reuse the same guy over and over, setting his fields. So you never have to change the byte buffer index very often. You generally, the offset and the length you bump as you parse along, and then you probe with the same object. Periodically, the object misses. You now want to stick it in the table, and you need to copy the bytes because you're going to recycle that byte buffer because it's NIO, and he's going to double buffer back and forth. So you make a copy of the fresh new string you've never seen before, and you insert that in the table as a string-like thing.
So you have a byte buffer to string map, and then as the lookup key, you're using a mutable byte buffer, changing the
I'm using a string-like thing, which is mutable. That's the main hack.
But that's backed by a byte buffer, and you're
it's backed by the byte buffer, right?
And you're reusing the key.
I can send you guys my file that I used for the tutorial for this shit. I have to go.
Have you ever recorded this class, or you give it live?
I've certainly recorded it. I've given it live. I can do the 15-minute version here, but it's kind of, it's got some slides. It makes it obvious what's going on. Then there's some code, and there's not a lot that you need to see. It's like you don't use buffered line read line to get a string out because that is an allocation for every line in your CSV. The usual thing is I hand people out a 2 GB CSV file. That's from an old fintech file that has this classic behavior of, it's got a bunch of columns, a bunch of numbers you're going to pull out. It's a bunch of strings. They're highly repetitive. They're kind of semi-random. You don't know ahead of time what strings you're going to get. It has all those sort of right properties. And then I step them through, hey, here's how you parse it. And by the time we're done, you have a single-threaded parser that's 5 times faster than the obvious good parser that people will start with. They start with a bad parser, they make a good parser, and then I get a 5x speed up by doing like the right shit. Let me pull stuff out here. I will throw in rocket school classes. We're doing like memory bandwidth here. Bandwidth. Here's the thing, and I'm not going to hand out a 2 gig file. It's on Dropbox. I might be able to hand out a. Where is the big one? Oh, Dropbox is saving space for me. Thank you very much, and not having the file be stored locally. Copy Dropbox link.
Well, it figured, why should I allocate all this space on your disk when I can just keep a pointer to it over the network where it already is?
No, yeah, okay. Maybe it's in there. So there's the Java file. Let me go pull the Java file up so I can look live. I can actually put it up on my screen here if I want to point people at it here. Oh, let me increase my font and shrink my window, and then go to, we'll try 14. I'll be giant enough here. Zoom. Where is share? Share. Emacs.
So yeah, the take home is that with the string creation, it will never be hot enough to avoid escape.
So this technique I'll show you here doesn't do the string creation. Whether or not there's an escape event going on is kind of up to the JIT. You write it this way and you don't have to worry about it. This will only matter if you're doing lots and lots of string creation, which looks really cheap in all the profilers and looks really cheap in the garbage collector and actually crushes you for performance. So the file says up here, driver number 1 loads a simple CSV reader, makes a pass per analytic. So in theory, I'm doing 3 different analytics. Okay, this is like a straw man. A, do only one analytics. So, driver 2 does only one analytics. Driver 3 says, okay, load things as lines and don't treat it like a CSV reader, which read that string line, parse fields. Then I do a couple more things after that where I'm cleaning it up as you go. And I get the bytes per second or lines per second here, ending up at about 1 million lines a second of reading, where every line is, a K or something. So I'm reading a gigabyte a second or something in this particular setup. It's just getting big enough to get really exciting here. And the final ratio is, 4.8 to 1, which is my number 2 version, not my number 1 version. So there's a main driver to help people time. There's a driver 1 version, which does obvious things, which says, make a new CSV. We're going to look at this. Read a line, split it, pull some things out, source some products for fintech data, count all the actions and count all the new products, run again through the products, compute buy, sell amounts and ratios. Third pass, find order quantities, work and execution quantities for the active trades that were going on in there. Okay, so it does some stupid analytics with mins and maxes and eventually standard deviations and such. So whipping down to what a CSV here is, it's been a while since I did this. Here, CSV line here. Okay, so CSV says, hey, I'm a class, I have a buffered reader. There's your buffered reader. That's the guy to avoid. New buffered reader read line. I have to read the first line and pick out the headers I'm interested. They're like 70 columns. I only want 6 of them, 7 of them. I read a line, I count my line reads, I split the line, calling line split on comma, and then I'm walking down the columns with not looking at read line for a column here. I'm looking for the columns in question. So go back up here to my driver 1. And I said, I look for the CSV has an index for the source column, index for the product column, index for the buy sell, index for the order quantity column, work quantity, execution quantity, so on and so forth. So I came up with some column numbers. I got an array here for the row, which is an array of strings, which I do the lookup and I pull shit out. And then I do whatever max quantity analytics does, which converts strings to doubles half the time and does mins and maxes and shit like that. So we'll look at max quantity and just see it doesn't do anything exciting here. Integer.parseInt, parseInt, find the max, total quantity bumped. Here's another one using a str object, which is a string-like API thing that's not a string. ParseInt does the same exact analytics. So the trick here is I never make a string if I don't need to make a string, because I want to reuse the storage space of the str objects for every line through. And this is where all the time goes. The analytics, the parseInt, this is no time at all. These are nanoseconds per whatever. So the main trick for CSV is that it does the wrong thing and how it gets the data pass. Let me go find number 2 here. Number 2 just does all analytics in one pass. It's still doing it the wrong way to get it. CSV to read line and split. I come back with an array of rows, which I pull out the 6 columns and I do my math. I have a little filter, by the way, as well, so I can avoid doing some of the work. But this is not the work. The filter and the analytics, that's not the work. All the work is right here in read line and split. This is where all your time goes. All right, go driver 3. Driver 3 does the first time I do something exciting with the data path. And this is read line for columns instead of read line and split. I get a line back. I do my line count. I pick out a column from it. Still have my column ID right here. So I don't know, the column IDs are all variant according to the file that comes in question. And I have another API to go get columns out. So instead of getting a row, an array of strings back for the row elements, I'm picking out my columns one at a time. And then I do all the same analytics I did before. And this is already like a 2x speed up, 3x speed up, just change the API very slightly. The business math looks almost identical. It's very similar business math. The underlying data path changed. So let's look at read line for columns here. What goes on here? Wrong guy. Did I get the right guy? Read line for columns on CSV. Yeah, okay. So he's calling read line, which is a buffered reader read line. That's the bad read line. But instead of string split, okay, what's string split do? Well, string split makes me an array of strings. So instead of string split, I'm doing index of comma, and I'm walking through my columns.
So string split is not only allocating an array, it's allocating each of the strings.
Yes.
Okay, that's a lot of allocation.
If I come in with a 128 byte line, it's actually like a 1,000 byte line of 70 columns, and I call string split, I get an array of 70 strings, I get 70 strings. Every string has 64 bytes of padding, slop, overhead, two base mark and class words, a car array, a hash field, and maybe some padding. And then you have the car array 2 words, and you have a length plus the string, which is 100 bytes. So it's a couple more words. So you took the bytes that you got from the string content and you added, I don't know, I did like 8 or 10 words. You added 600 bytes of overhead. And then you did the array, which meant that you had a pointer to the string and the array content, plus the array itself brought in, 2 more words and a length word and some padding and yada, yada, yada. And you end up with a 10-to-1 ratio of overhead to string content, something stupid like that for string split.
But creating strings out of a string doesn't necessarily create a separate char array.
It does as of the.
It depends on the version. So, and now it's byte array anyway. So it's, but okay. Yes, you're right. At some version they were making so much memory, so they started copying it every time. I remember that.
Yeah, they went through variations where they shared it, and then fairly early on they went to copying it every time, because people would make a string pointing into a giant buffer, and then the buffer would never die, and the giant buffer would be huge, and the string would be small. So they copied it every time for the longest time. So I claim that this numbers were correct up until maybe 2 years ago, and now I don't know. I have to go.
Split and regex did get special treatment because they were hazardous without extra string creation.
Yeah, regexes here aren't sort of the problem. Regexes, in my opinion, are a mistake in almost all situations. Very few times do I actually believe you want a regex. However,
as far as
we agree on something,
colliding strings.
Yeah,
that's one of the bugs that I've recently had to look up, which is, what's up with this string.
Right. So let me put my opinion out and walk away. Regexes are bad for a variety of reasons, but they can be made very efficient, but they're not a great API. So I want to go finish up this job, and then we can beat on regexes if you want. The key thing that I want to walk away from is this stupid piece of code here. It's stupid and it's small. And yes, it's obnoxious extra code that you have to deal with one time, and you throw it in the background. It's in your library. You never think about it again. It doesn't have to change. This is not a thing that edits a lot or mutates a lot or whatever. It just handles splitting out columns incrementally, one at a time. And then it updates it gives you an actual string right here at line.substring, but only on the columns you're asking for and not on all 70. So this one is still making a lot of strings. It misses out on the string array, and it misses out on making, 60 out of 70 columns. So it does cut way back. Then they go to round number 3.
But it is pretty generic. Like you could put that block of code into some standard parse tools library.
Dun, ta-da! Yes, you could. And in fact, H2O parser has essentially this code thrown away, a little more clever about the comma. Don't actually make a string object. There's a couple more hacks coming, but you get the idea. Like the actual string column splitter is a little smarter than just a comma check, but
You have to deal if it's the string is a comment, it can contain some commas.
Yes. So the string parser for H2O handles quoted strings and unquoted strings and strings with spaces and commas embedded and dashes and all the usual things. Like there is no real spec for CSVs, and H2O will typically read a terabyte CSV perfectly correctly every time, no matter what the fuck you do in there. And people do fucking ludicrous things. I have some really cool examples of CSV files that are ugly. So
almost makes it tempting to implement awk on top of H2O.
Yeah, right. You could do that. That's part of the fun games there. So raw CSV reader is the new reader, and this is the one where I start to actually not read the buffer.read line. And I get my columns out. The API is just the same. I skip to line start instead of read the line. I do raw column, which is pulling me out strings still, but I'm not going to do a buffered read line in here. So let's go look at raw CSV. Raw CSV extends CSV, except that I'm going to call the super to go read that first line using the buffered reader, and then I close it, and I never read it again. And then I can open a file input string and make a nice reasonably sized 32K byte buffer. I call fill. Here's the next piece of a thing you throw in a library for reading large text files. Fill says, I may have a partial line that I have to copy from the end of the buffer to the beginning because I only read partial of a CSV. So there's a fractional line problem you have to deal with every 32 kilobytes. Then I fill the buffer, reading as much as he'll let me read it a shot until the buffer's full, or I hit end of file. Then I have the skip to line I call once per line iteration, where I do a bunch of nitpicky math. And this is the same kind of nitpicky math you get in the standard NIO readers for Phil and Mark. Go look at how that code goes. They have some good documentation. It's the same kind of thing though. He's looking for, do I have a pre-computed end of line? If so, I can skip to it. Otherwise, I have to hunt for it. I have to hunt to the end of the next line, and then I set my position marks so I know where the line boundary is. And I guarantee you I have a line in the byte buffer, or I called fill. And that would guarantee me a line in the byte buffer. And then when I call raw line, I call raw line in, or raw column, I'm going to go get a column and make a string. And I have another version which does it with a string set instead of the str-like thing set instead of the reading of the column. And what's raw column imp will do? Same thing as the other guy above did, except instead of index of and substring, I just return you the positional elements for the string. So those 2 pages of code, that's the entire hack that you need to have somewhere in a library that you never look at ever again once you've debugged it, right? And you could totally take this shit and wrap a library around it. There's a string-like thing, which says I behave like a string, except I have a byte array int offset length bits that I can set. I have a toString in case I actually want to make a string out of it. It's great for debugging. I have my hash code identical to the string hash code. I have an equals. I have an equals to take a string so I can mix and match how I like. I have the copy and compress. I have a parse int on it. That's the end of the file. So let's go look at the raw guy. Raw column, raw CSV. How about raw CSV? Yeah, here's the raw CSV reader. Very same business logic as the prior guy. Here, let's see if I can make the screen wide enough for people not be ugly. It's probably wrapping too ugly to not help here. Where is, I don't want this one. I want driver 3 on the right. Nah, it's not wide enough. Let's make a string. How big can people go here? Driver 4, if I can type here and stare at my screen. So you know, I shrink my font. Driver 3 and driver 4, left and right. I don't know, that's probably too much. So here's the raw on the left and the regular on the right. Get your lines, for I equals 1 to n, skip it or read a line. If I didn't have a line, break. Source is I do something and I filter here. Source is I do something and I filter. Get my strings on the right, which is just, you know, go pull my columns out one at a time. On the left, pull them out one at a time. Do your business math, go on. So it's a almost perfectly identical business math, except the data path has changed, and that's your big speedups. The number 5 version is the same as the number 4 version, except that when I stick things in the hash table, the hash table is indexed by str objects instead of by strings. And so if I find that I've missed, data is null. So I do the lookup in the hash table, prods.get of a str object called a product, a string product. If I miss, I compact it, which means I've made a copy of it as a str object, but it doesn't have a backing by the byte buffer. It has a private array backing. And I jam it into the hash table, and I make a new replacement str object. So in these files, this 2 GB file, I probably have, there's like 1,000, there's a million rows, a couple million rows, and roughly 1,000 unique products. So I get a 99.9% hit rate. So 1 time in 1,000, I have to make a new str object here. This is the only allocation that happens. This and the new product showing up. It's the only allocation that happens during the run. And then I do my same business logic as I did before. I just count things and the buy, sells, and the max quantity. None of that's changed. So yeah, all of that was just, you know, long-winded way of saying, you know, memory bandwidth like burns you up when you start allocating furiously on a big thing. And CSV files, in my experience, have been one of the easy ones. Log file parsing as well. One of the easy big ways that you get large repetitious text for which you do not want to do allocation once per X, where X is big. You know, X is, hey, every byte that came in from memory, well, I made it twice to make it into a string in a buffered read or read line. I made it twice into a string when I split it. I made it again to an array column index. And then I did my lookup and I threw it away. And I got a 6-to-1 ratio, except I added string headers and string tails and padding a string and array strings. And it turns out that in this case, I get about a 15-to-1 ratio of byte read in to allocations when I start. And when I finish, of course, I get nothing. And then that gives me a 5x speedup. So there's your short version of the bandwidth section of this class. This class is like 2 hours long. This goes like 30 minutes. I get a little more AV, and I hand people the file and make them run it on their laptops.
So show us raw call again.
I'm sorry?
Show us raw call again.
Yeah. And I handed out the link to the file. So raw call is a wrapper over raw column impl. So the stir version calls raw column to get the column offset and sets it in. And raw column says columns are indexed in order, so I'm only parsing monotonically forward. You have to ask for the columns in order, so that's a little funny game. That's a little extra constraint. Just does a position. There's your local variable for your buffer, and now you know this is things that the JIT will do, except I'm forcing it by hand, so the JIT can't fail me now.
I was just making sure that you were caching the position.
Yeah, right here. Position is loaded up. Position stored down.
I see.
Okay.
that's an old trick, except you know, we had this thing where we'd take it out of order, but if it came out of order, we'd always start at 0.
Yeah, you know, back and forth. I decided to go with, in this case, it's easy enough to guarantee yourself an order, and a single assert catches your mistake, and then you load them up in order, and it's fine.
Perfectly reasonable.
If you had 100 different things and they're kind of randomly selecting, you didn't really know, I might choose a different API for how I got the things because I didn't necessarily want them. But you're going to parse through all the columns. If you need 100 columns, and you're going to parse through them. So
we did the same thing with linked list as well. So we had a linked list that had array speed, basically. You know, O1 access.
By jamming the linked list in an array?
No, by just caching the last location.
Oh, you're talking about, so you couldn't scan it fast, but you could jump to the tail of the linked list and add to it.
Well, yeah, head and tail were obviously 01, but if
Yeah.
you iterated it, like if you iterated it, or if you
It's
treated
the
it
list dot
as
get 7, right?
right, list dot get 7, list dot get 8, list dot get 9, it would work the same speed as array list.
Same asymptotic speed, because unless you do something else, another part of this class, I talk about the difference between array list and linked list, and I give you the big speed up numbers for using array list versus linked list.
I'm telling you though that there would be no arrays, there would be no speed up, because this linked list implementation would cache the last index number and the last element.
If you do a for loop as opposed to random access.
Oh yeah, randomly
Yes.
screwed.
Yeah. So here buried in the class notes, so I can throw the link in for class notes here. Oh, where's my CSV? Why are you not? Because you're kicking it up in the back.
And generally speaking, if you're using a Java linked list, you
Yeah.
probably shouldn't be employed in our industry.
Yes. So example one, linked list versus array list. And what's the difference here? I give the demo online. Okay, so yeah. So when the linked list is smaller and it's random versus not. So the other piece is if you make a linked list all at once, the elements are typically in order. If you then iterate it all at once, the x86 will prefetch you. And an array list versus a linked list in that case is like 1.5 times faster. It's not hugely faster. If you go random, you get a lot more, it gets a lot more ugly because the layout of the linked list makes you dance around. If you're caching like you're saying there and you have a forwarding pointer from the last guy, then it helps. As your linked list structure, the element count gets larger and starts to exceed your various cache layers, the array list gets sort of asymptotically faster, up to like 4 times faster, 5 times faster, because the linked list semi-random ordering just like crushes you for always cache missing. If you have them only accessed in order and you've got some sort of caching going on, then maybe life's easier. I'm doing both lookups. I'm walking a linked list and walking the array list and visiting all elements either randomly or in order. Big speed ups for array list in general, but bigger if they're bigger. All right, that's fine. I can hand out the lecture notes if people care, and the code if people care. This code is easier to run because it's self-consistent. The other guy needs a giant ass data file to show it off, and it doesn't have one happy here. So here's just a linked list, array list testing thing. Where's the links? There's the other one. Yes, cool CSV parser. Yeah, if you're looking for big CSV parsers, look at the H2O one. It does a couple other tricks besides being exceedingly flexible about what and how it parses. It's also exceedingly fast. It will also compress the shit out of the CSV data and present it to you in a compressed, big ass compressed table with fast parallel distributed access to it as well. So you have to eat H2O stuff there. If you eat H2O, you have to eat it all at once. So you're in for a penny, in for a pound with H2O, which is kind of unfortunately what's going on there.
Next topic.
Yeah, but say, well, how did we get here anyhow? It's fine.
Well, all right. So back to that. So you're saying that you have 1,000 data elements for 1,000,000 rows. So that's like saying 99% of your floats are 0.
No. No. 99% of them. No. They're all different. I have 1,000 unique products. Each product has a trade on an exchange. That trade is at a certain price point. That trade went through or eventually got canceled or timed out. That trade had an order quantity. It had a trade, it had an amount that was actually sold out of the total quantity that was up for sale or buy at that price point, and so on and so forth. So it has 70 columns worth of interesting facts about the trade. And you typically want to group these trades by product because products have wide variations between products, but very similar within a product.
So think about it this way, Jim. His CSV is what, first normal form, and in memory, he's third normal form. Did I get that right? He's deduping in memory, basically.
Yeah. And then I can do math across all of the sale events for that product. This is, 1 day's worth of trades for these products, right? I hit the admit button. Come on, let me in. So any one given trade product had on average 1,000 trades, but some of them will have 10 and some will have 100,000 trades on that day. And I like the cute dog better there, Jan. And then I want to find, for instance, the min and the max of the set of sales, the total count of things that sold that changed hands, the average price point they changed hands at, things like that. So it's not like they're all zeros, they're all interesting data.
Yeah, so the cheap row cache I have. So when I read CSV, I convert it to ISAM. So I no longer have strings in my data converting to numbers. But I have an API that uses text no matter what. So I find myself doing unending double, a 2-string double, back and forth. So,
yeah.
using the tiny little cache actually speeds it up. Going from null checks, type check, etc. There's 3 or 4 places in my code that uses this textual JSON, WebSocket API that only accepts text. And so the question that comes up over and over again is if you touch references, weak ref, soft ref, whatever, are you already paying a penalty versus just manually doing the accounting with arrays yourself?
The issue with weak and soft references is you're asking the garbage collector to know what you intend with the lifetime of the thing that you have. And that's sort of the danger, is that the garbage collector really has no fucking clue what you intend to have here or what you expect the future behavior of these fields to be. So
if you went in and added soft ref values that let you control, cache ordering, eviction ordering, etc., would it still be a waste of time at the end of the day?
I wouldn't go that route because you give up too much of what it means to have control here. So one of the fun things that happened to H2O back in the early days of the Azul collector was it's perfectly legit to clean out, I want to say, a weak ref if it's unused at the moment, or only weak at the moment, at any given moment. And the Azul collector was very cheap to do full GC cycles, very cheap. They happened a lot, which meant that if your ref when it's weak at any point, it got stripped out pretty quick. And a common bug was people would have was they would create a weak ref, shove it in the WeakHashMap, and then go get it out again. And in between putting it in and getting it out again, it got stripped out. And they were not prepared for it to be stripped out. And it just meant that the garbage collector and the semantics were not perfectly what you expected. So asking the garbage collector to run an LRU algorithm on your weak or soft refs because you're trying to decide when to get rid of something or not is not a great idea. If you want to have an LRU or a time-based caching where I've had this string for a long time and no one's used it for a while and I want to get rid of it, be explicit. Put a current time millis on there and say, periodically I have a sweeper thread that walks my table. Anything since the last LRU time of blah, blah, blah seconds ago, I toss. Or, you're not running forever. You have a finite lifetime and a finite size pile. You just keep them around forever. keep them densely packed, however you parse them. I don't know, ISAM is a good way to store it, but read the file, put it in some dense format, leave it around the entire duration of whatever you're trying to accomplish, and then the big garbage collection in the sky happens when the OS whacks you. Does that make sense?
Sure. Yeah. I've, come to that conclusion myself that, soft reference is probably not going to be controllable, even if you went in and edited it in the VM itself in C++. You're not going to get any better guarantees than your own, as you say, double accounting with a timer or whatever.
Right. And if the things are small and you don't have, too many, you just hang on to them the whole time. It's not worth throwing away. Like you're throwing them in a hash table because you're going to hit in the hash table again and pull them back out. If their actual size isn't too big, you got a few million, fuck it. Leave them around till the end of the program. Don't do accounting. That's more expensive than it's worth. Counting matters for throwing away a lifetime of things and caches because you had to have a cache because you couldn't hold all of them. If you hold all of them and you get a cache, it's the entire state.
I think the strategy would be to look at, runtime free memory and start the pressure on the eviction manually rather than trusting the reference manager.
This is what H2O ended up doing for our big data math. It's a pain in the neck. Much simpler if you didn't have to go there and you just pre-allocated your heap big enough to handle the size of the problem. But if you have to go there, you have to go there. There's APIs for the callbacks that said, hey, I would first, by the way, diagnose that this is your problem. You have a problem that says, I can't actually hold on to all of them. There's too many. Even if I get rid of the repetitions because I'm doing, caching and everything else, I got too many, I can't hold on all of them. Now you need a cache. Now I need to deal with evicting the cache. Otherwise, I wouldn't ever screw with it. I would say it's too cheap. My engineering time costs dollars. I will pay a bigger dollar to Amazon for a fucking 64 gig heap instead of an 8 gig heap. And an 8 times larger problem goes away. That's how I would approach it. Sometimes that doesn't work and you have to deal.
The other interesting thing that depending on what you're doing with the data, you have basically two axes. You have rows of columns, but you can also have columns of rows. And when you go columns of rows, it makes it much easier to deal with types, because instead of storing it as character data and then converting it expensively every time, you just keep an array of double. Now, what happens though, if you're processing row at a time and you have it organized, it's the age-old problem of XY versus YX, right? Because if you're processing row at a time, then you have no memory locality across the columns of a row. But if you are, for sake of argument, you're not using Java, you're using C, having it in a column format lets you hand it off to the processor and say, do something dramatic, with this chunk of memory. And, so you can use the AVX 512. Well, no, you can't anymore because they just removed it. But you can, in theory, if you buy an older processor, you can use some of the bulk processing stuff. And actually, I just read last week, you can use AVX 512. It's actually still in there, but you have to trick the computer by pretending that the efficiency cores don't exist or something.
So the H2O approach on this was slightly different. It was very close. So it read the CSV, turned things into 2D table, but it was column oriented. Then the column compression was typically so good that your memory bandwidth drop for having columnar compressed data exceeded all other costs. And the act of walking it row-wise wasn't so bad because x86 would prefetch each of the columns independently. And the columns themselves are all 10, 100 times denser per column, depends on how the data was. Floats don't compress well. Strings compress really well if you turn them into an intern table and just have an index number for them. And you got the compression wins all, memory bandwidth wins all here. So if you're going to read a big ass pile of text strings and doubles, I would put the doubles as doubles in a column, just like Cameron's saying, put the strings in an index table, put a number on the string, and have one column of numbers that are pretty dense integers and one column of doubles. And now you have an easy conversion back and forth in all directions. And a low cost in terms of memory bandwidth. And just hang on to all the data. Having, armchair general do a problem without actually seeing what it is, other than very brief description. Reading, yeah, I didn't do the live demo of reading 2 gig file. I should though. It's very. I have to go figure out how to trick Dropbox and giving my 2 gig file back. I would have thought Dropbox would have given me a fake link that would be a click through to make the file reappear. I wonder if I cleaned that up at some point in the past. I'll deal with it later. All right, yeah, maybe it's time for something else. WeakHashMap, yeah.
So I guess one of the things I've been interested in is this thing called fusion. So the idea is you have an algorithm that iterates over the data structure, and then you have like a simple thing that just adds all the numbers together. And then with the fusion, it combines these two together so that you get a single algorithm.
You're talking about
that iterates over it and adds the things at the same time.
You're talking about loop fusion?
Well,
Yeah.
it's more. I mean, it's data structure fusion is what the stuff I've been reading. So like because like the thing that iterates over the data structure, what it creates is a linked list.
Okay, so slow down. So back up for a second here. So throw something throw a link in the CSV and blah, 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 whatever in the doc. But
Okay.
you have an algorithm that produces a linked list. That's a sort of a non sequitur. An algorithm is a mathematical description of how you're traversing, doing something, whatever. Producing a linked list is a very specific version of things. You could produce an array list. You could produce any number of things. You could pre-cook whatever. So as soon as you said, I produced an inefficient, poor choice quality output, as Cameron says, if you're making a linked list, I don't know why you're working here. And then you're going to walk the linked list to do something cheap with it. Step number 1, don't make a linked list. Walk the cheap thing, do the cheap thing on the result as it comes out. And now you're talking about, is this a compiler optimization? You're asking compiler to do this? That's a variation of a compiler doing loop fusion, but with a data structure fusion or data structure as well. Then you don't actually fuse. Usually you just fuse the loops. You don't fuse the data structures. You discover that the linked list is dead and you throw it away. That's the hack. But I'm not making sure we're talking about the same thing.
Well, here, I put a link. I checked my references again. It's actually called deforestation now. Like that seems to be the more common. So, but
in fully recursive languages. Oh, yes, fine. Yes, okay, fine.
I mean, it's a functional programming thing. Like it doesn't even make sense in a strict language because the evaluation order in a strict language is fixed. And so
No.
data structures have to be
back up. Always the as if rule applies. So the evaluation order is strict. You must evaluate in this order. But if you can't observe that under the hood, I secretly did something in the JIT, you have no fucking clue. So, strict is not the issue here.
Yeah, but that's like saying that, being a sufficiently smart compiler should be able to optimize my program.
Yes.
To not use any loops or something.
That is true as well, and has been the case for the last 50 years, and they've gotten slowly smarter. Not necessarily claiming that this one comes up all the time. Here's a guy that's doing.
Yeah, they'd get better faster, except smart people know not to work in this part of the industry.
There are issues working in here, that's for sure. Well, that's because So don't people making linked lists all the time. Don't be
the
making
thing
a linked
about linked
list.
lists is that linked lists are a very convenient data structure.
Only
Like,
if you have a
whatever-
language
No.
which makes them convenient. Make
No,
them
so-
fucking called
Can you
linked list, and
So
they're
if a linked
inconvenient. I'm
list,
sorry.
if a linked list requires a single allocation, then it's not a linked list. It's something whose name is linked list. So Java's linked list is not a linked list. It's just an allocator tester.
Yes.
It's a de-optimizer for the JVM.
Yes. Yeah, I
And
get
Josh,
it.
Josh Block is a billion times smarter than I am, but that was a class he should have never written.
No, I understand why you wrote it too. It's too many people will demand it, so you have to. It's still, but you're correct. It's so bad.
Yeah.
I mean, the concept is bad and the use is bad. Fine.
Well, right, because the reason we use the reason we use linked lists in a language like C is because it costs us nothing, right? We put another 2 bytes or 4 bytes on the end of a structure. We have another linked list. We want another one. We add 2 bytes. We want another one. We add 2 bytes. Right. So what's the cost of a linked list? It's a couple bytes per node, right?
As long as your
Java,
count of
it's-
nodes is small, then you're correct. And I've done plenty of that in C, and you're right. It's
Right.
really cheap. Yeah.
Right. But in Java, it's a new allocation per node. So if I need, a dozen linked lists of nodes,
Yeah.
that's 64 bytes times a dozen
Yeah. The
per
overhead,
node,
right.
right?
And that's
So I
because
have
the
a
language
kilobyte
doesn't let you
overhead.
do the layout things you can. in C.
Right.
Yeah.
Well, you can't inline objects, right?
Yeah. And you can't inline objects.
I think the concept is fine. It's just the implementation, like both in Java and like in the hardware with all these memory latency effects. The concept itself is fine.
Of
Just
course.
the implementation is
As a
unfortunate.
mathematical entity, it's fine. The asymptotic costs of linked list versus array list are fairly large. They're 2x to 5x, depending on how big your linked list is. So it's pretty big. That's what Cameron's going to. The overhead of writing it in Java requires a lot of code. The C version actually requires some amount of code, but less, because you can object inline your way all the way around it, even to the actual implementation writing with like macros to make it happen magically on fields.
Exactly.
You go to a
Exactly.
pure functional language. So I'm looking at this paper here. It's a pure functional language. Oh, they hide the linked list constructor and the recursive everything. Everything's a linked list. It's super easy to write. It still has the same overhead costs as you get out of the Java version. Everything's an object. Everything's an allocation. There is no object inlining. There is no cheap version of it. Immediately, the costs are 2x to 5x, although the programmer costs to write and read them are low. So for
Yes.
small programs that are complicated and you're trying to get it correct, great.
There's no reason that everything's an object has to mean everything's an allocation.
Yes. Yes.
Like I could have a rectangle.
Yeah.
And it could have an upper left point and an upper right point and a bottom left point and a bottom right point. How many objects is that? It's 5 objects, a rectangle and 4 points.
Yeah.
How many allocations is it? It could be one allocation of a
Just one,
struct that has
Yeah.
4 numbers, left, top, right, bottom,
Yeah.
right?
Yeah.
2 X's and 2 Y's.
Yeah.
Right. So you can make an arbitrary number of allocations look like a dramatically larger number of objects.
Yeah.
At what point is the crossover from like 5 objects in a stack, in a singly linked list or stack, versus creating an array where you already know you have asynchronous re-entry happening? Say you're parsing HTML headers. So you got a buffer, you're creating indexes, but you don't know if you've got all the headers in the first buffer. So where do you
That's the parser I just threw out at you. You start parsing as you go along, and the whole reentrant thing is sort of a non sequitur. You hide it down the layer that says the buffered reader read another buffer and rolled the pointers forward so we can keep parsing. That's hidden at some low layer. This is all about, like, are you actually worried about the cost of parsing the HTML headers, which could be true, but they're not directly typically a big cost unless you have a lot of them. And if you have a lot of them, then that's what you're parsing. So sure enough, make a bigger buffer to read them.
Well, do you want an array during reentry? You get the next packet and
Yeah.
you
You keep saying reentry, and it doesn't necessarily
and-
mean what I think it means. I don't know what you mean by reentry.
So I've written like, full packet parsers on select.
Yeah.
And like you recommend not using strings, just parse out the indexes, line endings, and
Right.
the colons.
Right.
But you don't know the size of the packet coming
Right.
in. The first one may be Nagel, so 128 bytes.
Right.
You barely get the first header. So I built a pair class and just pointed one to the next to be done with it. Because typically you're not going to have more than 3 on that stack, but you can't guarantee you're going to get them all at once. So my idea, whatever, 10 years ago, was this new thing, escape analysis, is going to catch my pair class. And since these are not intern strings, it's almost free when the stack unrolls.
So that only works if they actually got caught by escape analysis, which in practice is fairly weak. So I would very carefully confirm that you're getting the escape analysis you think you're getting before you guarantee it, before you rely on it. Escape analysis fails for a variety of stupid things that are non-obvious when you write the code. And any place that it may have an exception, it may decide that it's too complicated to stack allocate and then unwind in the exception path and rebuild things in the heap and so on and so forth. I would take some care before you decided that you're going to go that route, before you believe escape analysis.
Would it be hard for the compiler to tell you how the escape analysis came out?
The vectorizing guys have been trying to get compilers to tell them that vectorizing worked or failed reliably for 40 years. So there's no good handshake where you're interested in a particular escape analysis happening or not, and you want the compiler to give you some kind of error. You're writing Java code. The Java C is not going to do escape analysis. It's about the JIT, right? So somehow you're trying to push something through the bytecodes that hits to the back end, that when the JIT finally happens and the high performance one, the interpreter, they escaped all the time. So everything was failing out in the interpreter, and including you leaked all kind of root structures in the interpreter immediately because everything escaped. Okay, fine. Now the escape analysis finally ran, and you've tagged some allocation that you thought should die in some particular scope or another. What's the reporting mechanism?
It's runtime.
I'm sorry?
The JIT discovers this at runtime. It cannot statically guarantee you that we will escape.
Profile data somewhere, in the land of Azul. When I did that web server backend, I brought out all kind of stats. I wasn't doing escape analysis then, so that didn't come out, but that would be the place I would hook code, and you would have to go look at your method that you thought was the hot method that surrounded blah, 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 and you could see, and here I escape analysed you and said that you didn't escape, so you got stack allocated. And crucially stack free. That's the other half of that has to happen.
So basically you would end up with a data center full of JITs that are all throwing statistics at some JIT DB stats
if you were looking
thing.
at this from a Google point of view and you're trying to say, on average, am I getting the escape analysis behavior? Like escape analysis gives you performance in a statistical fashion. The hack I just did for the CSV file, that's a statistical improvement. If 1 in 1,000 guys allocates in that iteration instead of reusing, you don't care. It's statistically you won. And in fact, you win at 50%. Right. So now you're grabbing statistics. You're asking me, when do I want to do this? Well, if you want escape analysis for Google, you need the statistical properties across your data center. If Jim's solving a problem for himself or his client, he wants it right here, right now for this point. And how does he detect that he's getting it? In the land of Java, you could count, for instance, string allocations run a heap profiler and count how many strings get flow by during every GC cycle. And if the count is high, you might be guessing that you're not getting your escape analysis you think you are. And then you could sometimes track those back, again, using a profiler to where the heap allocation happens.
I don't know if those cases are actually that different, though. If I dump a lot of the information that JIT learns into a database, I can locally say, run all my tests, let me look at some of the JIT stats output, or I have a data center where I'm running it on 100,000 machines and they are all sending giant arrows back.
Yeah, if you
show
get,
up in an observability tool.
Right. The issue there is you still have to get the JIT to cough up his internal stats in an externally readable way.
Well, and also you have 100,000 machines, you have 100,000 methods compiled on any of them. It doesn't matter for the most of these compiles that some escape analysis didn't happen.
Right.
Likely you're interested in a few which are in hot methods. First, you need to identify those and then see whether the important thing happened.
Right.
So,
and the trick there is the profiler will say it's all generically weak because it's all memory bandwidth cache misses, and the garbage collector will say I'm really cheap because I'm just young gen GCing furiously in microseconds, it's all fast, and you're out of memory bandwidth. And so if you see those two patterns of high rate of allocation, very cheap garbage collections, you're probably churning memory very rapidly. The next thing to do is assume you're out of memory bandwidth without running the hardware tools or hardly annoying to get going. Run a heap profiler and look at the places where you get the highest rate of allocations that are dying young. So, right, so you can go straight to a heap profile on a standard tool and it'll say, this site is allocating furiously, and you go up the call chain a few times, this is in a loop and you're allocating, and then you know it's getting thrown away. You think it ought to disappear. It's showing up in the GC as a large kind of, like the semantics are now tricky. If the profiling tool successfully reports an allocation, but it escape analysis, it disappeared, and it's not the cause of your large GC cycle. So you have to tease apart successful escape analysis that are still allocating. When you say, give me the heap profile for allocation rate, those will show up, versus what's tricking the GC into being full? What did he collect on? So you need to take the GC delta to delta runs that he'll give you. These objects died in this GC cycle, delta to delta to delta. You can see, oh, I get a lot of these things. Okay, where do they come from? I haven't successfully made a technique that works that I can teach other people. I do this time to time. I seem to be doing something different every time.
Yeah, I see how you can do that one-off. I'm less confident in how you can turn that into an observability tool that you can give the public.
The major trick is I assume escape analysis has failed, and and occasionally it has worked and it messes with me. But I assume it's failed. I see the high allocation rate and I see the low GC cost. I assume bandwidth. I go to the profiler. I come up with the hot allocation sites. I look at them and I assume that he is not escape analysis. I hack the code so that manually I do whatever it is, object pooling. My stir hack for the CSV, that's a one object pool essentially. So I do something like an object pooly like thing, and then I observe that GC times go down, like overall runtime goes down, GC cycles get further apart, and generally now there's a new allocation site I have to go whack after. But in like that CSV,
so that one object pool is escape detection.
The object pool is me manually doing escape analysis. Is that what you said? I've done.
Well, it feels like you're not doing escape analysis as much as escape detection. I am detecting when the thing has escaped and only allocating then. It seems like a kind of laziness.
Okay, the technique I'm using when I analyze somebody else's code for performance starts out by assuming escape analysis is going to fail. I do my profiling and the various things, and I come up with, oh, I think you're out of bandwidth, and it's due to an allocation. And I go hunt up that allocation. Then I assume this allocation I'm looking at is in some hot loop. There's a lot of them. Maybe put some counters and run again, verify that I'm getting a huge count of them. That's the same as the profiling tool says counts. Escape analysis maybe isn't working because they show up in the GC side. So I manually put the object pool in. Now I run again and go again, and there's no escape detection. It's my head is said, I personally analyze this code. I assume that the compiler can't get a perfect analysis going. I say I can, I'm going to manually hack it. And I'll handle all the off branches that the compiler doesn't like, all the escape paths, the exception throws that he's confused by. I'll handle them all manually. like the semantics can change. You know, if you do an escape analysis and you stack allocate an object, then you throw an exception in the middle and you have to manifest that object, and you go to manifest it, but you're out of memory. So you now get an out of memory during the exception throw of an object you should have already allocated, and you cannot allocate it. So now you have changed the program semantics. This is a testable change of program semantics. I can write you a JCK test that will fail. It will claim it's allocated an object. It will then throw it out of memory, allocating that object in reality at some point where it can't have done that, except that, so yeah, there are some issues there. And this is one of the reasons why, for Jim's sake, why I don't trust escape analysis to work. I did an escape detection technology separately that worked reasonably well. It was pretty decent. It didn't really win against the good Azul collector. Although in some of these cases I'm talking about now, it might win against the Azul collector. Back in the day, I didn't have these examples in front of me. It's harder to pull them out.
Yes. Speaking of this issue of having to allocate an object which was previously unavailable in the exception path. So at first, we were careful about implementing this, and we were looking whether the object we're about to scalarize can be accessed in the exception handler in the current method. But I think we found some wording in the spec which can be interpreted that we can just pop the frame. If we cannot materialize the object in that frame, we can pop the frame and propagate the exception to the outer frame. I don't remember the exact wording, but we had this discussion, and yeah, it seemed that okay, we can do this kind of thing.
You have
similar
to
what Stack Overflow does.
Similar Stack Overflow. But so you have to make the object at some point. If I've made the object in theory, and in theory I've escaped it.
You need the object only in the object can only be observed in the exception handler of the method which allocates it.
Okay, fine. Yeah. So you're saying you don't even do an escape analysis if somebody cheats and pre-escapes it. I mean, the hacks for Stack Overflow that are checking that you get this correct all pre-escape their objects, so that and at that point you give up on all escape analysis things anyhow. You don't care anymore.
So yeah, you can check whether the exception handler accesses the value which you're about to scalarize. But right. I think you can just, if you cannot rematerialize the object, I think the wording in the spec allows you to just pop the frame and propagate the exception further without running the exception handler in this frame.
Oh, on Stack Overflow you can, yeah.
Yeah, I think the wording in the spec is generic enough so you can do it for other exceptions. I don't remember it.
Oh, the JCK test this very carefully. Stack Overflow behaves as if an exception got thrown at a particular point, and all semantic changes before that point are entirely observable, and all semantic changes after that point are not observed. So you can't have any missing loads and stores floating around. You can't have any sidestep this or that. So Stack Overflow walks the knife edge, and 100% guarantee. He may, in theory, in practice, he actually runs on a little ways before he finds the overflow, and then when he decides to go throw the exception, when he starts to throw it, he has to toss the current frame and make some space, but then he discovers he doesn't have enough space yet. So he has to keep tossing frames. He tosses side effects that went with it as well. And that he just really prevents the side effects, and then he starts throwing at some point, carries it on as if you got there in the first place. So he plays the knife edge game.
So it doesn't throw as the last save point. It just throws as some previous save point.
It actually throws the last save point. He just guarantees that the last save point happens with enough space to throw. But in practice, you might have made several frames past the last save point, as long as they don't have any observable side effects. So when the unwinder comes along, he throws a frame and says, can I go? Do I have enough space? No, I might throw another frame. He's going to go as past some save point that he got to, that was declared as the point at which it's going to happen. Then he takes the code from that save point up to the throw point, allows it to have happened, with no side effects there because there weren't any, because that's how the definition went. And then he jumps. So you can only throw at certain points as a consequence. And the usual thing you can only throw at is at a method entry. And the method entry guy has a stack probe, he does. And stack
Did you get the
probes-
bugs out of that process in less than a decade?
I did.
Whew.
I did. It was not, you're correct. There were a couple years where it was buggy, and then we did a hard push and got it out at Sun, and at Azul, I cleaned up that path a lot. That was one of the paths that I cleaned up majorly in the runtime, made it a lot simpler. So it can be done actually fairly simply in the end. You have a probe page, you have 4K past the probe page for the handler to run as well. The probe page, you get 2 pages at the end. That you don't have to probe on the probe page unless your stack frame that you're about to allocate is more than the size of a page, which is 4K. The x86 4K pages. So if your stack frame is less than 4K, you can walk into the probing frame normally, and the rule is you have to touch the frame before you hit the next safe point. And if you touch it and it blows, you haven't hit a safe point, you haven't got any other side effects that are safe point observable, you can go back to the start of the method entry, which is itself a safe point, and you're good. So you can't have a safe point on entry and some other safe point that's in without probing the stack. But the probe can be an accidental touch from anything. And if your frame is more than 4K, you have to probe them all. And at that point, we inserted probes, and we had to probe every frame, because you could have 16K, you stack allocated a 16K byte buffer because you're inlining a NIO method. He's got a 16K local buffer. You don't want to probe 16K in because you went past the 4K guard and the next 4K guard. You went past your 8K of guard, and you can't do that. You have to probe 4K to shot. So you take the frame, you put probes in at 4K to shot. If all the probes passed, you're good. If you're under 4K, then anything counts as a probe. Anything that touches the stack counts as a probe. That's how it ended up getting sort of cleaned up. Is it nasty thing? Yes, but not ultimately very expensive once you got all the corner cases knocked out. And then when the unwind came, he threw away the frame. I think he could go to another safe point, but he could go to your stack frame that you took it on entry and blew on and run from there. He definitely was allowed to throw multiple frames away, and there was a time when he did. And I think now at Azul, at least, I think I got it to where he just tossed the loser. Like he had space for some amount, but he decided he didn't have space for until the next safe point amount needed more space, and he would toss you in. It's ugly. Yeah, Arthur can tell me I'm all wrong now. Or it doesn't work that way anymore.
So, that all sounds close enough to what I've seen. And essentially, we do the same kind of trick with other exceptions if we couldn't allocate the object in the exception handler if we needed to rematerialize. At first I was opposed to this because of the same reason, like it's changing observed behavior. But later, other folks convinced me with quotes from the spec that you can actually interpret it this way. Unfortunately, I don't remember the exact wording and exact details.
I'm with you. I think you're allowed to throw some frames away on a Stack Overflow, including having some observable side effects that get tossed.
Oh, but the Stack Overflow is clear that you can do it. But the question was whether you can do it with other exceptions if you cannot rematerialize some of the escape eliminated objects.
Right. General runtime versus out of memory. Like I think maybe even out of memory has even more caveats or more freedom.
Yeah. So essentially, it's not any exception. It's an application threw an exception.
Yeah.
You went to this path. You needed to materialize some objects, and then materializing these objects, you ran out of memory.
Yeah.
And that's the question, like, yeah, can you pop some frames out so you can propagate the out of memory now without materializing the object? And currently we do. We pop the frames if we cannot materialize previously eliminated allocations.
Okay, and then you're going to throw stack out of memory.
Yeah, yeah.
Exception gets
And then-
converted to an out of memory.
Yeah.
Yeah. That's one of the fun Java special griefs in the world. I throw an exception X, I get an out of memory exception, not an X exception. That's legit by the spec, and okay. All right, what else? We beat this one down.
And you can never really have a function that you annotate as like, this thing is not allowed to ever throw. So the compiler can be more aggressive because
Yeah,
out of memory can always throw.
Yeah, I would like to claim that that's a doable thing in a language spec.
Oh, we have this optimization. We speculate that a call doesn't throw, and if it does, then we de-optimize on the return from this call instead of propagating the exception via normal means.
Oh, yeah, that's been around a long time though.
Yeah, maybe it exists in C2 as well.
Oh yeah.
I think we had to add some infrastructure around it. That's why I wasn't sure if C2 had it.
No. If I have a function call I'm going to make, and I've inlined it, and then it throws somewhere in there, I give you some valid stack frame that may or may not have that execution of that function may have triggered the exception, but the throw you get will be always on or before that exception. And then maybe the throw is I just deopted to the interpreter, and the interpreter, blew up. Somebody says I'm allocating a negative array. I've inlined you and inline, da. Somewhere along in the way, I do a range check against, length is less than 0. That throw you get anywhere before the length less than 0, and I'll just deopt and run on in the interpreter.
No, the optimization I'm talking about, if you have a call, it's not inline.
Oh, you're not going to inline it. Yeah.
Yeah, it's not inline call, and then you have to have an exception handler for this call if there is an exception handler. Yeah. But we can speculate that we've never seen this call throw an exception before. Right. So we will not emit the exception handler in the caller, but instead we'll mark this call as deopt on throw. And if we need to propagate an exception, the unwinder will need to turn it into interpreted frames and then propagate it on the interpreted frames.
C2 has the same effect. I don't know if you're using the same words for the same thing. Certainly, if I have a call, I'm wrapping a call with a handler. The call wants to throw. The handler's never executed before. The handler that gets installed is deopt to the interpreter, and let the interpreter deal.
You mean that it will be in? So you will have the handler, but the handler will just deopt
immediately. Yeah, right. Yeah, I won't actually run any handler bits. The kind of story, if the exception, well, it's fine. If the handler throws in the past, then I am strongly motivated to inline the throwing function into the handler, so I can turn it into a computed go to. But if the handler's never thrown, typical story for me, if the handler's never throw, I don't emit any code for them. I deopt just straight up.
Yeah, I think it has similar effects. We just have this cut line at different places. You have the handler, but the handler is immediately de-optimized. We don't have the handler. We de-optimize on.
Have the handler, right at the JIT level. I mean, at the machine code level, what a handler is, there isn't. I don't have a handler which does Java exception handling per se. I have a set of addresses that you get jumped to on an exception of some kind that did a stack unwind that he then does something stupid with. Like if it's a real handler, he probably starts looking at an instance of whatever. But I just jump to some address that's the handler address, and the typical handler address is deopt. And that one is actually so common, it's commonly shared, and everyone just jumps to the same fucking deopt handler with a different pointer to go get your metadata from, and you're out of there. So I wouldn't claim it's a Java handler that's wrapped to a deopt. I'd claim it's the deopt handler. But
yeah, it should be equivalent then. Yeah.
Yeah, right. This comes right. At some point it becomes a difference that makes no difference. What I was looking at, see if there's some new topic I wanted to bring up here. Here's an array list of this versus array list of that. What is this? Oh, what is this one? Why is array list here?
Oh, sorry, that's what I wrote. So I would like to bring up a new topic about the escape analysis. Object allocation.
Yeah.
So I find that this is a very common pattern to use exponential increase
Yeah.
No, for the a buffer.
Yeah.
So let's say that the initial size is 10,
Yeah.
and inside a loop you put a lot of objects in this container. Let's say it's like a array list. Sometimes you run into some kind of okay, it's full, so I have to increase the space for this buffer. So Java actually lacks of resize or reallocate like we did in C or C++. You know, all Java objects, all Java array is immutable. Somehow it's immutable. So if you want to have like a bigger array, you have to reallocate this array and copy from the original one to the new one. But you know, I'm thinking of what if we can have like an internal API in Hotspot to resize this array. And the algorithm is like this. I check this. I check the remaining space in TLab. If say that we still have a lot of space in TLab, I can go there and change the array size field of that OOP and say that I make it 2 times faster, 2 times bigger, and just like we did that. In this way, we can avoid some kind of array copy.
You have to have no allocations in between. Or
yeah, exactly. So we need to guarantee that this object is the last object you have allocated.
Yeah.
So the point is like this. So this kind of like pattern happens everywhere in a array list, in StringBuilder, in the like string.join.
Oh yeah, it's a real common pattern because it has the reusing in place is not changing the asymptotic performance. It changes the constant factor. So people start with saying asymptotics are better, I don't care. Now it's an optimization only to update the TLab directly. And it only works if you haven't done any other allocations like that new node. You went from size 8 to size 16. First, you made 8 new node objects to fill it up. By the time you go from 16 to go to 32, you're not adjacent. You've allocated right afterwards. You can't do a reallocate in place.
So we actually do have this exact optimization. And
how do you do it with the allocations from the nodes versus the array itself?
So the way it is structured, I have a special node, basically realloc in place. This node, then I have an optimization which looks for a pattern where the source of the allocation, the source of memcopy is not used after the memcopy, and source can be reused.
Right.
So I convert it into this node which attempts to realloc in place, and then this node in runtime, it checks the TLab. If it can extend in TLab, it does it. If it can't, it just does normal allocation and memcopy into the new allocation.
Right. And what I'm asking is the apparent behavior of the common use case here would say that there's always an allocation and you could never reallocate in the TLab directly.
Yeah, that's my initial thought actually. But if you think that this kind of like a buffer incretion happens inside of a loop, you know. So it's very possible that, you know, the last allocation is this array. So, you know, in the next iteration, you can safely put it in the, you can assume that this array object is the last object.
Okay. I would say that you directly don't get this in a loop. That instead, what you can get with a loop is you can pre-count the number of allocations and pre-size.
Wait, but why don't you think it will work in a loop?
Okay, so let's write some piece of loop code here. I'm going to extend your guy here and just for a little code. For int I equals 0, I less than n, I plus plus array list dot push of new node of some sort of function on I.
Remember to share your screen while you're typing.
I put this in the doc.
Right, but anyone
Change
watching the
it to
video
push.
won't see it.
Oh, good point. Let me do that. Share screen with Google Docs. How about now? Okay, so I added the for loop at the bottom. And if I'm going to repeat the for loop with inlining of the push operator so that we can see the interleaving going on here.
Interleaving.
Well, yeah, I immediately see that you have new node allocation here.
Uh-huh.
Yeah, but so for us, the motivating example was to have a fallback for StringBuilder optimization. So we have an optimization where we try to do try statically produce better code for extending the StringBuilder, basically pre-allocate the buffer. But if it fails, we have this realloc in place. And for a StringBuilder, it doesn't have this issue of an extra allocation.
Okay, yeah. No, whatever, arrays dot, whatever. It's not array copy of. There's a size of an array.
Actually, I came this example from the StringBuilder. But I can see that one side is Cliff's example has like a new node. That's one allocation. The other side, you can see he calls like a function. So function may have like side effect. They might allocate a lot, right?
Yeah, but that is why the way we have it, we have a compiler optimization which replaces an allocation and a copy into this allocation with a special node, which in runtime checks whether there is space available in TLab and whether it can do the extension. If it can't, it will do a normal allocation.
Normal, yeah, that's so far my idea. And the other idea is, I can identify this kind of like idiomatic code pattern, and so try to do the allocation in a specific area, because I know that it's very possible that we need to resize this array in the future.
The assumption with string buffer is just wrong to start with. Because it only has two modes. String buffer, I know it has more methods than this, but no one has ever used them outside of the TCK. It has basically two methods: append to the end and turn it into a string.
Yeah.
Right. And so all you're really trying to do is optimize append to the end. Why would you ever copy data to append to the end?
Yeah.
Why would you?
Well, when you need to the existing implementation of it will do.
But you write the VM. Don't tell me about the existing implementation. You own the existing implementation. You're God. Like, you do whatever you want with the existing implementation, right? So first you allocate 8 bytes, then you allocate another 16, then you allocate 32, but you never copy. You just create a kind of appender node, and only when they say toString do you ever have to copy anything.
So the asymptotic costs here are the same. I hear you, do not copy the data. The asymptotic costs don't change. If adding a bunch of appender nodes maybe works for as the string builder gets very large. And I think you're right, though, that it's just append and toString. So maybe, I don't know.
Right. The problem is that you copy the data log n times.
No, but the data gets exponentially bigger, so the asymptotic costs are the same. You're paying a constant factor per byte copy.
Yeah, I can't do math, but I think you're right.
That's the well understood, and it's very observable. You pay a constant factor per node. It's not per byte. It's not.
So where do the pointers to all these allocations live?
So if you just do it, the copy thing, you only have the one pointer to the one array, and you're doing what I'm inlined there. You just make a new array that's a copy of the old one, double the size.
So what Cameron suggests is to use a linked list here.
Yeah, it doesn't have to be a linked list. It can be an array list of appended objects of doubling in size byte arrays or car arrays. Yeah,
I'm saying have a current append node and then some other structure for you need a collection of prior byte buffers and the current one you're working on, and when it runs out, you make a new one that's twice as big and you add it to the collection. Yep. And then toString walks the collection in order. And that
you don't have to chase down the linked list and turn it into a log n access instead of a log 0.
No,
They go
when you're
0.
to string, you're going to copy
Go
the
one.
data one more time into a contiguous array. And it's a linear walk. You only walk login elements of string headers, but you've already allocated 2 to the x amount of stuff, so the cost is constant again. I claim the cost is the same cost you get by doing the copies with the array copy asymptotically. There is some constant factors change a little different. I don't think.
So yeah, I guess there is a solution on the JDK level, just to change how this thing is
Right.
structures the data. But I think the pattern of reallocation of some underlying like array is common enough to target it as a compiler optimization.
Yeah.
Like, yeah, it will not work all the time. And Cliff has an example with allocation in between where it will break.
I claim there are 2 ways to tackle this kind of thing, both of which you could ponder doing. One is, as soon as you see an array list hinted at as a thing that's a doubling buffer, move its allocation into a different TLab from where you're doing your other allocations. So it has a bunch of space. Basically, you're pre-allocating a bunch of space for it that you hope they're going to use when it grows again. And then you have 2 TLabs running now, and eventually you have to decide it's not going to grow anymore, and you're just going to take it over and finish out the second TLab. But you get some chances to reallocate in place. The other one is to say I have a loop over a doubling. Look at the loop trip count. If it's a counted loop, and nearly all loops are counted loops. If it's a counted loop, I have a count for the loop and just pre-allocate.
Although wait, if it's by counted, do you mean compile time known count? Like constant?
Runtime known. Upon entry to the loop header, you have a known trip count. So 0 to n is trivial, but anything that says lower bound to upper bound by constant stride, this excludes while loops, while some predicate, not counting those.
Yeah, so it can be, so you'll have some kind of, the overall length will be a function of the loop trip count. Because it can be doubling, it can be doing something else, but if you can like come up with a closed form for it,
right?
And you can
C2 tries really hard to come up with close. That's the range check elimination. C2 does really hard to get a closed form solution for the trip count. That's his range check elimination. So any arbitrary lower bound, upper bound, and stride that are loop invariant, he'll take as a trip count, and he'll do monotonically increasing for range checks. He's a little more looser for range checks. He can handle monotonically increasing, not just loop invariant.
Yeah, I think both of the ideas are interesting extensions to this realloc thing. But what I also want to add that, yeah, that asymptotically, like you are improving the constant, and it gives better performance on small, like for StringBuilder patterns on small ones. Yeah, you are saving significantly, but when it gets large, you're not resizing that many times. Like you're resizing log n times.
That's the asymptotic cost. Yeah.
Yeah. So it's this optimization is of a limited scope.
There you go. So here's the cost analysis, by the way, for people who haven't done this before. If I see a byte and I throw it in, I'm going to call it a cost of 1. If I copy a byte, I'm going to cost it another 1. So the first bytes that go in get copied a lot, but the last bytes, the last half of the buffer that gets filled up, only got a cost of 1. The first half of the buffer got a cost of +1 to get to the last big guy, plus all the costs they had before to get copied. And it turns out you get a tail off, a total power of 2 tail off. The last half of the time got a cost 1. The first half got a cost +1, of which half was just that, and the other half got another +1, and so on and so forth. And so you get an average cost of 2 over the entire buffer, because it's a sum of copying it 16 times and copying it 8 times and copying it 4, 3, 2, 1, 1 times 1 byte times 16 times whatever. You'd end up with a cost of 2. So that's the only thing that's useful here is if you're growing the array hugely and you have other issues, you sometimes want to grow by 1.5 instead of by 2. Then your cost is 3 instead of 2, but your slot pad that you lost at the end is half the size.
Yeah. So when we did this for large data sets, we would grow, I think, either by 12.5% or by 25%.
As long as you're geometrically growing, you're okay. Yeah. Yeah.
And that what that allowed us to do is, and then you could basically shift gears at some point if you wanted to. So you could reify everything to your left into the first buffer of a new series. So if you were worried about object, because basically you have two things that you're balancing against. You've got bus limit and you've got, object count limit, right? And, so as long as if you're avoiding the bus, you don't copy. If you're optimizing over time for GC, you reduce the number of objects. So, we could have a system with, 100 trillion objects in it. And well, from the user's point of view, 100 trillion objects, and it might only be, 1 trillion or something. Like you could dramatically reduce the actual number of things that the GC had to deal with.
Another one for Java is you have array size limits.
Yes.
2 gigs divided by 8 byte pointers puts you at a couple 100 million objects in an array.
Yeah.
Before he'll.
You can almost get to 32 bits.
Yeah. Yeah, if you live with 32-bit pointers in a 4 gig array, I don't think Java ever made it to the 4 gig array though. So if you live with 32-bit pointers, you can get twice as many.
2 billion, well, 2 to the 31st minus some tiny number.
Right, and then divide it by the 4 bytes or 8 bytes, and that's how many elements you put in an array list before he runs out. Yeah, which I've totally fell over the edge on.
No, I think it's always 2 billion. Like even if they're larger values, you don't lose those.
It may be the case in recenter years in the 64-bit VM, you can have 2 billion elements at 8 bytes per, which makes your object array some kind of gigabytes, which was beyond what the garbage collectors was handling back in the day, where back in the day was not that many years ago. They strictly wouldn't allow you to, the runtime wouldn't allow you to create an object. Please, Mr. Runtime, allocate me a single object independent of all garbage collecting, a single object of more than 2 to the 32 bits, 2 to the 31 bits.
Yeah, that was certainly true on the 32-bit VM. So.
It was true on the 64-bit VM long after I left.
Can you not index an array in Java with a 64-bit int?
No, you cannot.
It's only 32-bit.
Language declared as an int. But it's worse than that, Jim. He's dead now. You have to shift and sign extend it to 64 bits once you get past that size. And Intel doesn't have any of its addressing modes do that directly. They'll do sign extend shift or shift and sign extend. They do it the wrong way. So you have to add an extra instruction in your hot loops if you may see an array and an array index that's more than 2 to the 32 after scaling. So if you have an array that has more than an index of 100 million or 150 million, 120 million, and a 2 gig array, or it's maybe 4 gig array, and you shift scale add, he'll wrap that number unless you put a manual and extra JIT inserts an extra sign extend in there. So all the addressing mode calculations, which are in the core guts of every x86 generator on the planet, get screwed with if you have to index into an array of more than 2 gigabytes in size. And that's the trick why it's painful. And separately, Java says, oh, and your indices are they're capped at 32 bits by the language spec. So you're going to chop it off. You have a long, you chop it to an int. If it goes negative, you got a negative array, you didn't get the larger value. So that's it. I'm going to stop the share here, I think, unless somebody's got something else going to do with it. If I can find the thing. Bam. Okay.
I would say if I was writing a language today, I would have the indexes be I64.
Yeah, right. Yeah. I mean, if you want to support big data anything at some point, 64-bit indices. Yeah, totally. I don't know. I could sort of kind of ponder. No, I wouldn't do that. You could ponder doing a 32 indexed thing where the max index value after scaling was fit in a 2 to the 32. But what that does is it saves you an extra instruction on your x86 for performance. Like it screws with the JIT to have the flip-flop between the two. And if you only flop and only insert it, it was a generation where it mattered. I don't know these days if it matters a whole lot. It'll pollute your iCache tiny amount. Probably x86 sees that pattern all the time for folks like C who do this all the time. So he probably optimizes the hell out of it now.
Well, to me, the question where it matters is, are you ever going to go back and support some 32-bit thing?
Yeah. Maybe, you know, if there's a code generator issue, I'm looking at emitting code for 32-bit ARM and a low power application. Yeah, there's probably a mode that says, arrays are capped at this. This will shave an instruction off of your array lookups for people who want to have a small form factor VM and a small form factor chip.
So like there is a micro Python.
Yeah.
Its goal is to make Python work on like microcontrollers.
Yeah, right. Yeah.
And every once in a while, you'll just trip over something. It'll be like, nope, this became a 32-bit number. Bye.
Yeah, right. Right.
Please handle the exception.
Right. Ah, nice to get an exception now, as opposed to just silent bad behavior.
Yeah, I was doing something with dates and I went past the 2038 and it was just like, there are no dates past that. And I was like, what? Oh,
it's a better
right.
answer than
time is 32 bits here, not 64.
Yeah, the other answer you could have got is, and it's 1777. And you're underage, sir. You're not allowed. Oh no, you're older. Okay, whatever. Fine, yeah. 200 ages. So let me know, Arthur, if you ever get the allocation interleave growth thing with the React. You two's in, yeah. Let me know if you guys figure that one out. And StringBuilder, I'm with Cameron. StringBuilder on is such a specific API with such a specific use case that the correct answer to do speed up there is to fix the constant factors in the Java code. If you have to go to the JIT to pick up some little tidbit, maybe whatever, but I'd go into the Java code and say, and here we're going to do a secret hack. I use StringBuilder a lot too.
Well, they did fix it on the Java level for concatenation of string literals, or like concatenation in the language, because it is emitted now as invoke dynamic, which has different strategies how to like implement this behavior. And one of them is to pre-allocate, like count how much memory you would need and pre-allocate it. So for this part, it's solved. Yeah, there's a lot of code which does explicit StringBuilder, and this is not addressed.
I do it all the time. I wrapped a StringBuilder, I wrapped a library around a StringBuilder, a class around StringBuilder called SB, and all the append things are one character long. It's way the hell easier to use. I don't say .append, .append, .append. It's a dot.
You will never wear out a keyboard, Cliff.
You haven't seen me type.
Oh, Cameron,
renaming StringBuilder SB sounds like a very Cliff thing to do.
Oh yeah, totally.
Cameron, I just want to say that for those developers, for those Java developers, some of them spend most of their time on their business logic. They don't want to spend a lot of time to digging into how Java is implemented or how JVM is.
Yeah, that's exactly what my argument is that that's the job of Arthur, to make all their crappy code run much faster. That's the whole point of having the JVM.
Yeah, if know, those people know exactly how the StringBuilder, the mechanism behind that, and so they can pre-allocate a accurate number of buffer, and then they can avoid this kind of repetitively copying things.
That's correct. But if they knew to do that, they probably wouldn't be in that job. In all seriousness, like if only the topmost guy, only the guy that creates a string buffer can make that guess, so it's like you have recursion, you have libraries, you can't. So yes, if you spend a lot of extra time and and have a lot of skills, you can pre-allocate the buffer perfectly. But your typical developer is not going to do that.
Yeah, I have another example. I got like a complaint about the rejects performance after they upgrade to JDK 17. You know, they show us some kind of example, and we spend weeks to debug this kind of thing, find the root cause. But actually on their side, they just refactor their code and try to get rid of those kind of rejects. Then they move ahead. They don't care about how the rejects is implemented in Java and how C1 optimize and this rejects code for them. They just get their application faster enough, then they can move on those their business logic.
Yeah, exactly. Yeah, I mean the level of performance optimizations we're talking about here, you know, you don't want to see those types of optimizations in a typical application because they're the problem is, you know, every one of those optimizations introduces at least 100 off by one errors, and I would personally get at least 65 of those wrong, right? Like, you know, so your optimizations, you want as much as possible to delegate down the stack, right? You want, obviously you want the APIs to allow you to make optimizations easily, but as much as possible, you want them automated. I mean, that's, yeah. So regex is it's a topic in and of itself, of course.
Did I miss the regex bashing earlier?
I'm fully prepared to hand everyone a suicide pistol to shorten the conversation. As soon as somebody says regex, everyone shoot that person.
Yeah, you know, the story is like this. So we found that C1 of JDK 17 is like 80 times slower than JDK 11. So for some kind of like specific regex, the reason is that they introduce a hidden class. Hidden class change some kind of invoke special to invoke interface. The funny thing is some regex generate some kind of like classes implements a common interface. So if you generate like IC call, which means inline cache call, so those classes trash this kind of like IC stub with their concrete class instead of the interface class. That's why, you know, we see a flood of like IC misses handling things for this reject. That's the story. I see that C2 has already dealt with this kind of like a special code pattern, but C1 doesn't. So so that's why we patch up the C1 to resume the performance. But the story is, you can see that they develop some kind, you know, the JDK became more and more complex, and it's very easy to get some kind of like performance regression.
So back in the day, there was, performance regression tests, and people hacking the JDK and people hacking the JIT had to coordinate on regression tests, regression failures, or like performance failures. You hacked your JDK, something else got slow. We went back and forth. You can't ship that JDK yet. What the hell happened? So I don't know. Sounds like a pipeline processing, whatever you call it here, a continuous integration workflow problem.
LLVM has the infrastructure to do this kind of performance regression canary, but I haven't found the similar things in the OpenJDK.
Certainly, an OpenJDK. Sun had it forever and a day. I assume Oracle has done something there. I don't know that OpenJDK did. That's a good point. I threw a link in
tried
there
with Oracle, but the legend with Sun was that you could show up to them and be like, here is my hard workload. And they'd be like, great, we'll add it to our benchmarks. There
were a lot of funny stuff. Yeah. If you were prepared to go cook it down to a benchmarkable thing, we'd take a lot of stuff. Yeah. I threw in a short StringBuilder link in there as well. It's hardly half a file worth of short links. That's it. Oh, I added a new API that StringBuilder should have. This is Cameron says, you only do append and you only do toString. There's one other one I do.
Is it go back 1 byte?
Yeah, roll back 1 or 2 bytes. So yes, exactly.
Ooh,
It's in
roll
there.
back 2 bytes. Fancy.
Sometimes
So
I have comma space as a separator instead of just
So-
comma.
And we do that on IO as well. It's one of the handiest things when you're doing JSON files.
Oh, yeah.
You clip the 2 characters off the end, and then you append a new record. So you can have very efficient log to disk by in JSON format.
In JSON format, I
without
see.
ever reading.
Yeah, okay. I wasn't typically doing that. This is me doing pretty printing of large, complicated structures.
But JSON on disk is basically pretty printed data structures. Right?
Okay, fine. Yeah, fair enough. Yeah, that's good. That's a good hack. I like that.
Yeah, I can show you an example if you're curious.
I think I got it, but maybe somebody else wants it. I'm claiming we're 2 hours in, and I'm going to call it shortly.
Good enough.
All right. Anything else? All right. I'm going to claim victory for the Alliance here, and see y'all next week. Bye.